Hello students, and welcome to the lecture on Control Unit. After this lecture, we will be able to learn the following objectives. Understand the instruction types. Understand the formats, instruction cycles, and subcycles. Describe the concept of micro-operations. Define hardwire and microprogram med control. Explain microprogram sequencing. Let's start with the introduction of Control Unit. A control unit is the subcomponent of the Central Processing Unit, or CPU, that manages all of the actions performed in this area in a computer. It is responsible for taking the various inputs from the computer, instructions and data, and telling the processor what to do with them. Since the CPU is considered the brain of the computer, Control Unit is sometimes referred to as the brain within the brain. Depending on the CPU's architecture, the Control Unit may have varied tasks to perform. The Control Unit is actually made up of several subcomponents. During the hardwired days, all of this wiring and circuitry formed what is known as a finite state machine, a system having a singular purpose in directing the operations of the computer. Separate circuits were responsible for decoding and encoding instructions, while others handled logic or counting the instructions the CPU worked on. Everything happened in order, where the logic circuitry would be flipped one way or another to direct the instructions to storage. An instruction is fetched and decoded, and then it needs to be executed in order, one after another until completion. In older CPUs, the instruction would have to go through an entire process and finish calculation before the next would begin. To speed up processing, modern CPUs use what are called pipelines, where each step is part of the pipeline. Let's now discuss instruction types. The instructions can be of shorter or longer formats. Shorter instructions take less time for fetching and decoding as compared to longer instructions. Unconditional transfer instructions. JMP, call, RET, INT, and IRET instructions transfer control from one code segment location to another. These locations can be within the same code segment, near control transfers, or in different code segments, bar control transfers. Jump instruction, JMP. Jump unconditionally transfers control to the target location. JMP is a one-way transfer of execution. It does not save a return address on the stack. Call instruction. The call procedure activates an out-of-line procedure, saving on the stack the address of the instruction following the call for later use by a RET or return instruction. Call places the current value of EIP on the stack. Return and return from interrupt instruction. The RET, return from procedure, terminates the execution of a procedure and transfers control through a backlink on the stack to the program that originally invoked the procedure. RET restores the value of EIP that was saved on the stack by the previous call instruction. Conditional transfer instructions. The conditional transfer instructions are jumps that may or may not transfer control, depending on the state of the CPU flags when the instruction executes. Conditional jump instructions. Conditional jump instructions contain a displacement which is added to the EIP register if the condition is true. The displacement may be a byte, a word, or a double word. The displacement is signed. Therefore, it can be used to jump forward or backward. Loop instructions. The loop instructions are conditional jumps that use a value placed in ECX to specify the number of repetitions of a software loop. All loop instructions automatically decrement ECX and terminate the loop when ECX equals 0. 4 out of the 5 loop instructions specify a condition involving ZF that terminates the loop before ECX reaches 0. Executing a loop or repeat 0 times. JCXZ, jump if ECX 0, branches to the label specified in the instruction if it finds a value of 0 in ECX. JCXZ is useful in combination with the loop instruction and with the string scan and compare instructions, all of which decrement ECX. General purpose data movement instructions. The MOV move transfers a byte, word, or double word from the source operand to the destination operand. Stack manipulation instructions. The push decrements the stack pointer, ESP, then transfers the source operand to the top of stack indicated by ESP. Push is often used to place parameters on the stack before calling a procedure. It is also the basic means of storing temporary variables on the stack. The push instruction operates on memory operands, immediate operands, and register operands, including segment registers. Formats instruction cycles and subcycles. The CPU performs a sequence of micro-operations for each instruction. The sequence for each instruction of the basic computer can be refined into some abstract phases. Fetch instruction, decode, fetch operand, execute. Program execution can be represented as a top-down design. Program execution, instruction 1, fetch instruction, decode, fetch operand, execute. Instruction 2, fetch instruction, decode, fetch operand, execute. Instruction 3, Once a program is in memory, it has to be executed. To do this, each instruction must be looked at, decoded, and acted upon in turn until the program is completed. Fetch cycle. The fetch cycle takes the address required from memory, stores it in the instruction register, and moves the program counter on 1 so that it points to the next instruction. Decode cycle. Here, the control unit checks the instruction that is now stored within the instruction register. Execute cycle. The actual actions which occur during the execute cycle of an instruction depend on both the instruction itself and the addressing mode specified to be used to access the data that may be required. Immediate addressing. With immediate addressing, no lookup of data is actually required. The data is located within the operands of the instruction itself, not in a separate memory location. This is the quickest way of addressing modes to execute, but the least flexible. As such, it is the least used in the 3 in practice. Direct addressing. For direct addressing, the operands of the instruction contain the memory address where the data required for execution is stored. For the instruction to be processed, the required data must first be fetched from that location. Indirect addressing. When using indirect addressing, the operands give a location in memory similarly to direct addressing. However, rather than the data being at this location, there is instead another memory address given where the data actually is located. Logic microoperation. Logic microoperation specifies binary operations on the strings of bits and registers. Logic microoperations are bitwise operations. For example, they work on the individual bits of data. Execution of a complete instruction. The program counter, as one of several different registers built into the CPU, performs the task of receiving each of the instructions in task sequence. Maintaining the logical sequence simplifies the forward progression to each step, ultimately completing the task. This logical progression is maintained by pointing to the data that is to be used next even as the previous data is in use, and then quickly pointing to the next data in the sequence as each instruction is executed in turn. Depending on the configuration of the program counter, the register may actually serve as the pointer for more than one instruction involved with a given process currently under execution. With some register designs, the program counter not only points toward the process that is next in the sequence, but also toward the just released instruction that is now in the process of being implemented. This particular design is thought to aid in maintaining the balance of resources, as well as helping to protect the forward movement of the instructions with a higher level of efficiency. The function of a program counter is essential to the successful execution of the instructions involved in any task. By pointing the way toward each instruction in the sequence, the counter helps to provide a logical execution of those steps that ultimately lead to completing the task quickly and efficiently. Without the use of this type of register, the potential for the sequence to be disrupted would be enhanced, and the chances for completing the task would be relatively few. By adding organization to the incremental step-by-step completion of all instructions, the program counter serves as the conduit that minimizes anomalies and keeps the process moving forward properly. Now we will study about hardwire and micro-programmed control. It should be mentioned that most computers today are micro-programmed. The reason is basically one of flexibility. Once the control unit of a hardwired computer is designed and built, it is virtually impossible to alter its architecture and instruction set. A micro-programmed computer, however, one can change the computer's instruction set simply by altering the microprogram stored in its control memory. In fact, taking the basic computer as an example, one notices that its 4-bit opcode permits up to 16 instructions. Therefore, one could add 7 more instructions to the instruction set by simply expanding its microprogram. To do this with the hardwired version of the computer would require a complete redesign of the controller circuit hardware. Another advantage to using microprogrammed control is the fact that the task of designing the computer in the first place is simplified. The process of specifying the architecture and instruction set is now one of software, microprogramming, as opposed to hardware design. Nevertheless, for certain applications, hardwired computers are still used. If speed is a consideration, hardwiring may be required since it is faster to have the hardware issue the required control signals than to have a program do it. Microprogram sequencing. The controller causes instructions to be executed by issuing a specific set of control signals at each beat of the system clock. Each set of control signals issued causes one basic operation, such as a register transfer, to occur. An alternative way of generating the control signals is that of microprogrammed control. In order to understand this method, it is convenient to think of sets of control signals that cause specific micro operations to occur as being micro instructions that could be stored in a memory. Each bit of a micro instruction might correspond to one control signal. If the bit is set, it means that the control signal will be active. If cleared, the signal will be inactive. Sequences of micro instructions could be stored in an internal control memory. Execution of a machine language instruction could then be caused by fetching the proper sequence of micro instructions from the control memory and sending them out to the data path section of the computer. A sequence of micro instructions that implements an instruction on the external computer is known as a micro routine. The instruction set of the computer is thus determined by the set of micro routines, the microprogram stored in the controller's memory. The control unit of a microprogram control computer is essentially a computer within a computer. If the map bit is 1, the logic attached to the multiplexer's select lines produces a 0-1, which selects the address ROM or ROM. Therefore, the address of the microroutine corresponding to the instruction in the outer machine's instruction register will be channeled to the control ROM. It should be clear that the map bit must be set in the last micro instruction of the fetch microroutine, since it is that moment that one wants the newly fetched instruction to be executed. Wide branch addressing. Generating branch addresses becomes more difficult as the number of branches increases. In such situations, programmable logic array can be used to generate the required branch addresses. Microinstruction with next address field. One of the most striking features of the microroutine is the relatively large number of branch microinstructions. These microinstructions constitute 1/3 of the total and present a serious constraint on the operating speed of the computer. The situation can become significantly worse when other microroutines are considered. The increase in branch microinstructions stems partly from limitations in the ability to assign successive addresses to all microinstructions that are generally executed in consecutive order. For example, in wide branching with address modification, some addresses have to be assigned in a rather inflexible fashion, and this frequently leaves addresses spaces that are difficult to use efficiently. As an alternative, one may consider a scheme in which each microinstruction includes some branching capability. The simplest approach is to include an address field as part of every microinstruction, to indicate the location of the next microinstruction to be fetched. This means, in effect, that every microinstruction becomes a branch microinstruction, in addition to its other functions. The major disadvantage of this approach is the need for additional bits for the address field. Its severity can be assessed as: in a typical computer, it is possible to design an adequate microprogram that governs most control functions with fewer than 4K microinstructions, employing perhaps 50 to 80 bits per microinstruction. This implies that an address field of 12 bits is required. Therefore, approximately 1/6 of the control store capacity must be devoted to addressing purposes. Even if more extensive microprograms are needed, the address field will become only slightly larger. In a microprogrammed processor, the control unit consists of control address register. This contains the address of the next microinstruction to be executed. Control data register. This contains the microinstruction to be executed. The sequencer determines the next address from within control memory. Control memory, where microinstructions are stored. Sequencer. The sequencer generates a new address by incrementing the CAR, loading the CAR with an address from control memory, transferring an external address, loading an initial address to start the control operations. Address sequencing. Microinstructions are usually stored in groups where each group specifies a routine, where each routine specifies how to carry out an instruction. Each routine must be able to branch to the next routine in the sequence. An initial address is loaded into the CAR when power is turned on. This is usually the address of the first microinstruction in the instruction fetch routine. Next, the control unit must determine the effective address of the instruction. Mapping. The next step is to generate the microoperations that executed the instruction. This involves taking the instruction's epode and transforming it into an address for the instruction's microprogram in control memory. This process is called mapping. Prefetching microinstructions. The major drawback of microprogram control is the inherently slower operating speed of the computer. Fetching a microinstruction from the control store takes considerably longer than generating equivalent control signals using hardwired circuits. Concept of horizontal and vertical microprogramming. The horizontal microprogramming is also called hardware microprogramming. The length of the microinstructions is high, and they control many hardware resources operating in parallel. To each resource of the computer, a field or bit is assigned, by which the resource is controlled. The meanings of the microinstruction fields do not depend on the meanings of other fields. None of the fields can have two or more different meanings for identical values contained by that field. The disadvantage of horizontal microprogramming is that the bits of the microprogram word cannot be used efficiently. Not all microinstructions allocate useful meanings to all the available fields. The vertical microinstructions execute simple operations such as load, store, add, branch. These types of microinstructions are similar to machine language instructions, which contain an opcode and one or more operands. This is the reason why vertical microprogramming is also called software microprogramming. Did you know in 1967, Fairchild Semiconductor introduced an IC that contained all of the ALU functions, but required additional circuitry to provide register storage and data control? Now in the end, let us summarize what we have learned in this lecture. A control unit is the subcomponent of the central processing unit, or CPU, that manages all of the actions performed in this area in a computer. The instructions can be shorter or longer formats. Shorter instructions take less time for fetching and decoding as compared to longer instructions. So shorter instructions are preferred over longer ones. The jump instruction always performs the same basic function of transferring control from the current location to a new location. Its implementation varies depending on whether the address is specified directly within the instruction or indirectly through a register or memory. The pop transfers the word or double word at the current top of stack, indicated by ESP, to the destination operand, and then increments ESP to point to the new top of stack. Pop moves information from the stack to a general register or to memory. The instruction fetch and decode phases are the same for all instructions, so the control functions and micro operations will be independent of the instruction code.